Ever heard of a data dandelion? Get ready for an aha moment, because today we're diving into the mind-bending world of using fractals for data storage. You know, those mesmerizing repeating patterns you see in snowflakes or ferns?
Yeah, they're not just stunning to look at. It turns out they might hold the key to storing colossal amounts of data.
We're talking massive, like next-level storage solutions.
It's a fascinating area, really, where nature's elegance meets cutting-edge tech. We're essentially talking about taking inspiration from the natural world to organize information in a completely new way.
We're looking at some Python code today that simulates this whole thing, but hold on, it's not just about pretty pictures on a screen.
No, no, not at all. This code actually simulates an AI learning to use a very specific type of fractal, a logarithmic Bloom fractal, to store and retrieve data.
A logarithmic Bloom fractal. Okay, that sounds kind of complicated.
It's based on, you guessed it, a logarithmic spiral, that beautifully simple pattern you see everywhere, from seashells to galaxies. The code generates this spiral, and each point on that spiral, well, that represents a potential place to store data.
So it's like a cosmic game of connect the dots where the dots are data points.
You got it.
But how does the AI factor in? It's not just randomly throwing data onto the spiral, right?
You're right, it's not random at all.
Huh.
That's the beauty of this code. The AI is actually learning the most efficient way to encode and decode that data within the fractal. With each iteration, it gets better at figuring out where to put specific pieces of data, kind of like it's figuring out the best spots.
So it's like it's learning the optimal filing system, but instead of folders, it's using points on this intricate, ever-expanding spiral. That's incredibly clever.
It is, isn't it? And you know what one of the most compelling aspects of this is? The built-in error correction. Since the data is stored multiple times on different parts of the fractal, if one part, say, gets damaged, you can still recover the information from the other locations.
Whoa, so it's like having multiple backup copies. But instead of separate copies, it's like it's woven into the very fabric of the structure itself. This
Exactly.
is incredible. So how much data are we talking about here? How much can we actually cram into one of these fractal structures?
That's where it gets really, really interesting. The code includes a calculation for storage capacity, looking at things like the number of iterations in that spiral, how much redundancy you need for that error correction, that sort of thing. And, well, the more intricate the spiral, the more storage you have.
Okay, so more complex equals more storage space. Makes sense.
Okay.
But this is all theoretical, right?
Well, about that,
Mm.
the code actually demonstrates this concept in action, using a sample sentence as data. So we're not just imagining this, we're seeing it work.
No way. A whole sentence stored on this fractal thing.
Yep, it's pretty amazing.
And to deal with all that, the code uses GPU acceleration. That's got to be important, right?
Mm,
Especially when we start talking about larger data sets.
absolutely. It's crucial for making this process efficient. We're talking massive data sets here. And without that extra processing power, things could get slow.
So instead of our computer working overtime, the GPU swoops in to help speed things up. I bet that's vital if we're talking about storing huge amounts of data.
100%. It's all about making this storage method scalable and practical for real-world use. But of course, there's always a trade-off.
A trade-off. Okay, now you've got me hooked. What's the catch with this whole fractal storage idea?
Well, think of it like this. When we make the fractal more complex, by adding all those iterations to the spiral, what happens is we do increase that storage capacity.
Yeah.
But those extra iterations, they also mean that the calculations, the ones for actually encoding and decoding that data, they become more demanding, more intensive.
So it's kind of like, I don't know, trying to fit more stuff into a suitcase. Like you can probably cram more in, but it gets tougher and tougher to zip it closed.
Exactly. That's a great analogy. It's all about balance. And that's something we've got to keep in mind when we start thinking about using this tech in the real world. Because the potential here, it's massive. We're talking about maybe being able to store gigantic data sets. I mean, huge, like entire libraries, scientific data, historical archives, all in a much smaller space than we need now.
Okay, now you're just blowing my mind again. So we could, like, have a library on something the size of a postage stamp. How could we even do that?
Think about it. The more we can compress the data, the tighter we can pack it, the more we can fit into a particular space, right?
Right.
So with this fractal approach, we're essentially creating a highly efficient three-dimensional storage system. And get this, imagine what this could do for fields that rely on huge amounts of data. I'm talking genetics research, where storing enormous amounts of DNA information is so important.
So potentially, we could be talking about shrinking down those giant data centers. And that means making them more energy efficient, or even changing how we think about portable storage devices. But this code we've been looking at, this is like a first draft, right?
Yeah,
A proof of concept.
exactly. It's showing us what might be possible, giving us a glimpse into the future. The code even shows the execution time for the calculations, how long it takes to make this happen. Now, that'll vary depending on the hardware you're using, sure, but you can see that with the right processing power, we can get some pretty impressive speeds.
It's just wild that we're at a point where we can not only imagine this tech, but actually simulate it. And then not only simulate it, we can see how long those calculations take. This feels huge, like a total game changer in how we store and use information. It's
Uh,
kind of mind-blowing. We're talking about storing data on a fractal, something that seems so abstract. But to think about actually holding it,
yeah.
having a physical thing, how do we even begin to build something like that?
That's where it gets really, really exciting. We're talking
Uh,
about potential breakthroughs in nanofabrication. Imagine actually constructing a physical storage device, but at the nanoscale. Essentially etching a logarithmic bloom onto a tiny, tiny chip.
Oh, wow. Okay, that's a lot to take in. It's like what, trying to like carve a sculpture, but on a grain of rice.
It's a huge technological challenge, for sure, no doubt about that.
Yeah.
But it's not impossible, not completely outside the realm of possibility. I mean, think about how far we've come, from those old punch cards to the tiny, powerful storage we have today.
That's true, yeah. It makes you wonder, are we approaching this the wrong way? What if instead of forcing these patterns onto silicon, we found a way to, I don't know, grow them organically?
Now, that's a fascinating idea.
Yeah.
Almost like we're growing data storage the way nature grows a seashell,
Hmm.
using nature's own solutions. It's tapping into the whole idea of bio-inspired computing.
So we're not just making things smaller, we're talking about completely changing how we think about storing information. It's like we're at the very start of something totally new, a new era of data storage where nature and technology are like woven together.
And who knows what other secrets are out there, right? What other elegant solutions nature has for us. This code, what we've been looking at, it might just be the tip of the iceberg.
So, to everyone listening, next time you're looking at the patterns in nature, the spiral of a pine cone, the veins on a leaf, you might just be looking at the future of data storage. This has been an incredible deep dive, and we can't wait to see where this tech takes us. Until next time, keep exploring, keep those questions coming, and as always, keep seeking out those aha moments.